All right, this is the beginning of the recording, Monday, April 27th. Oh, I need to move these back. I'm going to know what I'm going to say. All right. Okay. Let's leave it on that screen. Yep. Okay. There we go. All right, all right. 5, 4. Yeah. Okay. Welcome back. So let's I started recording. Yeah, I did. Okay. Here's the outline for today. I'd like to do these two warm-ups, do a round of announcements, look at some additional substitution integral problems, and then move into a new topic. That'll be like more than halfway through the class. New topic called definite integral, and then end on announcements again. So to do this warm-up first, okay. Uh, if you remember all these antiderivative problems, antiderivative of e to the 3x times quantity 1 plus e to the 3x close parentheses raised to the fifth power dx. These antiderivative problems are always about like the derivative of what is this thing. Well, and I don't know. Like off the top of my head, I don't stare at what I just circled there and go, yeah, the derivative of blah is what was just circled. So in those cases, typically what you want to do is do some substitution. So I'd like to use u is equal to 1 plus e to the 3x. Why is this going to work? Well, the derivative of u is the 1 differentiates to 0, but e to the 3x derivative is e to the 3x times 3. Where does this extra times 3 come from? It's the chain rule. I should mention at this point, sometimes what happens is because there's these steps where we're differentiating, these steps where we're anti-differentiating. You got to keep track of which thing you're doing as you do it, right? So we're differentiating e to the 3x, get e to the 3x times 3. How do you know what to pick for u? Generally speaking, you're looking for somewhere else in the problem. You're looking for the derivative. You're looking for, in this case, e to the 3x times 3. I don't see that times 3, but that's usually not a worry. That will usually kind of push in front of the integral somehow anyway. But this e to the 3x, I see that elsewhere, right? Because look, if u is 1 plus e to the 3x, that's over here. Then elsewhere in the problem, that's this part to the left, that's where I'm seeing the derivative morally. There's this e to the 3x even if there's not the times 3. So this seems like it's going to be a good choice for u. Once you've computed the derivative of u and you've written this as du over dx, this is the stage at which we need to solve for dx. The first step that you always do to solve for dx is you'll have to multiply by dx on both sides, because take a look, dx is in the denominator currently. So multiply both sides by dx and you have du is equal to 3. I just put the 3 in front now, but 3 e to the 3x times dx. And then to solve for dx here, we need to divide on both sides and have du over 3e to the 3x equals dx. Okay, so we've got our pieces here. Let's take a look at the original question, paste it back down here, and substitute what we can. So when we see a 1 plus e to the 3x, we'll substitute that with a u, and when we see a dx, we'll replace it with this fraction. Those are the only replacements made here. We still wrote the integral sign. Antiderivative of is how to read it. Right? Antiderivative of e to the 3x. It's real tempting to try to substitute this e to the 3x right now, but let's not. Let's wait. We replaced what was in parentheses with a u. We still had to write this 5 exponent to account for everything, and then the dx became the fraction du over 3 e to the 3x. Now take a look at the nice thing that happens. There's an e to the 3x in the numerator and an e to the 3x in the denominator. They cancel each other out. There's a 3 that's still part of this fraction in the denominator, so I just brought this all the way in front of the integral. You don't want a 3 in the numerator accidentally. It's still a 3 in the denominator, so it's a 1/3 in front of the integral. The e to the 3x is canceled out. So integral sign's still there because we haven't found the antiderivative yet. So we keep saying this antiderivative of. We keep doing these algebra steps of cancellations and so on. Integral of u to the 5th du. But now look what happened. We went from a problem that had all x's to this mix of x's and u's that didn't look great. But now we have a problem. We have this antiderivative problem that only has u's. And this antiderivative problem looks way nicer than the original one. But now we've put off antiderivative finding as long as possible. Let's find an antiderivative. The 1/3 you get to copy, and then u to the 5th. To anti-differentiate this, we're undoing the power rule. You raise the exponent up by 1, so you have u to the 6th over 6 plus c. So this is the stage going from here to there where we are now doing the integral, or we are now finding the antiderivative. So we went from what is the antiderivative of u to the 5th to saying this is the antiderivative of u to the 5th. It is u to the 6th over 6. Okay, and then one last thing, we need to replace the u with 1 plus e to the 3x. So we'll have, oh, I did one other thing. You don't have to. You could just leave 3 and 6 in two separate denominators, but I just squished this all into one fraction. Multiplying the denominators, that's where this 18 came from. Other than that, I replaced the u with 1 plus e to the 3x. There's still a raised to the 6th power to account for, and still the plus c was copied. Okay, so that's warm-up 1. I hope that looks okay overall for folks. The second warm-up question was this. So integral of, or antiderivative of, the fraction x over root x plus 6 dx. Okay, this one is actually going to follow the kind of general method we saw last Thursday. So last week on Tuesday, Wednesday, Thursday, we did substitution. On Thursday, we saw these problems where not all the x's went away right away. There was sort of this kind of uh-oh situation, but there was a way around it. So we're going to experience that in this problem. And in fact, let me say this about this question. This one is actually less involved than some of the ones we saw last Thursday. And I intentionally picked this one later because it's sometimes when a problem is less involved, it's harder to see what's going on. Because right? Like there's sometimes you need the extra moving parts to see what to do. So last Thursday we looked at, I would say, once this question is done, you'll say that the ones we did last Thursday are more challenging, but it's easy to follow visually the pieces because there's pieces you can follow along. So here let me say what I mean by just let's do the substitution. U is equals x plus 6 to take a derivative of u. Du over dx is, well, 1, because x differentiates to 1, 6 differentiates to 0, so I didn't write 1 plus 0, I just wrote 1. And now to solve for dx, as usual, you got to multiply both sides by dx. So you have du is equal to 1 times dx. I didn't even bother writing the 1 times part, I just wrote dx. And you know, as just like in the last warm-up, you have to multiply both sides by dx, and then usually there's an additional step to solve for dx. But take a look. In this one, dx is already solved for. If I step back to the previous warm-up question, we had to multiply both sides by dx to get here, and then dx wasn't solved for. We had to do one last thing, which is divide on both sides to get dx all by itself. Here, we didn't even have to do that. So in this question, just multiplying both sides by dx here, we're left with du is equal to dx. This is kind of unusual. We have actually so far never had a problem where du just equals dx, right? This is usually du and dx are not equal. And we needed to see lots of examples where these are not equal first, just to make sure. So let's take a look at the original question here. Let's make some replacements. So the time we see x plus 6, which is in the radical, that can get replaced with a u. And we'll replace the dx with a du. Again, it's unusual to replace dx with du. Usually, we've been replacing dx with some fraction. Dx has usually been du divided by something. But here, it's unusual. It's not what happens most of the time. It's a coincidence that du equals dx. So dx just got replaced with a du, and this x plus 6 in the radical got replaced with a u inside the radical. So we made the typical replacements of u and of dx, but not all the x's went away. So we said, well, let's try one other thing before switching it up and maybe picking a different u or something like that. Is can we replace this x? And take a look. We've got u equals x plus 6. If you just subtract 6 on both sides of this equation, you have u minus 6 equals x. So we can replace this x in the numerator with a u minus 6 instead. So for a moment, it looked like we were stuck with this kind of integral problem here where there was a mix of x's and u's. That doesn't look so fun. But actually, after looking back to how we defined u and substituting for x, we have now an integral problem that has all u's in it. Okay, that's good. Is this better than this question? I say yeah, because take a look. We can actually apply some algebra. This algebra step means we still need to write the symbol that means antiderivative of. And this algebra step looks very similar to one we did last Thursday. So we have u over root u, which ends up being u to the 1/2, same algebra as last time, minus 6 over root u. And so I copied the minus sign in the 6. And when you have a root u in the denominator, that will be a u to the negative 1/2 power. Still a du there. Okay, so the whole point of writing it in this format is we don't have this fraction anymore. We've, u over root u simplified to a u to the 1/2. Now the whole point is we have two separate terms. So we can antidifferentiate each of the two terms separately. The first term, the point is now we're ready to talk about actually finding the antiderivative. So this is the last time in which we write this antiderivative of symbol, because now we're reporting on what the antiderivative is. So if u to the 3/2, right, raise the exponent by 1 to undo the power rule. So u to the 3/2 over 3/2 minus 6 is copied, and then antidifferentiate u to the negative 1/2. So take that exponent of negative 1, add 1 to it, and you have positive 1/2. So u to the positive 1/2 divided by the new exponent. And then, since we're done antidifferentiating, there's this plus c. One last step, though, is we should replace the u's with x plus 6's. So making that one final replacement, this will be our final answer. Does that look okay here? I think the thing that I will just want you to be careful of is going from here to here is, I think, one of the more challenging mental steps of the process is finding antiderivatives. You have to do this eventually. It's either you take the problem right away and you go, oh yeah, that is an antiderivative rule that we learned before doing substitution and apply it, or it happens somewhere in the middle of the problem. But you do have to find an antiderivative, and that is, finding antiderivatives is one of the more challenging steps. So sometimes what people try to do is to try to combine that challenging step with the much easier step of just replacing u. In this case, all the u's getting replaced with x plus 6. That's not so bad, right? But like, just because replacing u's with x plus 6's isn't so bad isn't a good reason to combine steps. Like, I don't know if I would successfully get from this step right here to this step while skipping the step in the middle. There's just too many things going on. So it's not a place you want to combine steps. Just kind of one thing at a time there. Find your antiderivative and then replace the u's. Okay, I said what we would do next is do a little round of announcements. This is an exam week, so there's a online quiz Tuesday, so it opens at midnight tomorrow, available all day tomorrow. As part of an exam week, there's this pre-exam assignment, so I want you to inventory kind of what topics we've done since the last exam and what identify for yourself what things are challenging and how you plan on working on it. Thursday's an exam day, so that's the official date of the exam. So there will be no live class on Thursday morning. I don't want to just shove more content. Like we don't need to do that. Though Thursday's the official date. Again, with this setup, you can take the exam on Thursday. You can take the exam on Friday. In that 48-hour window, you just need to pick a 5-hour window of time to start and finish the exam. The main difference compared to the last time is to turn in a single PDF file. I don't want to belabor all these details right now, so please take a look at the PDF called Exam for Info, where those things are all spelled out. And get back to me if you have any questions about it. Sorry for the many emails, but just there were a lot of announcements that I wanted to clear up, and that's my uniform way of getting information to you. Um, Please start WebWork 38 today, and just as a reminder, those office hours are available. So what I want to do actually is still continue with some questions I would have loved to have asked last Thursday, but you know, Thursday had a sort of a different goal. So what I want to do right now is let's look at antiderivative of the fraction ln of x over x dx. I'm going to say that picking u equals ln of x is going to work. Now, why is this going to work? Remember, here we're taking a derivative. Sometimes people take u equals ln of x, and we'll take the derivative of that. I want to remind you back from like the 6th week of the semester that derivative of the natural logarithm of x is 1 over x. Now, so why is this going to work? Remember, when you pick something for u, typically what you want to do is the derivative of u, in this example, 1 over x, you're looking for that elsewhere in the problem. And I actually see a 1 over x up here, right? I mean, I know it's an x in the denominator. That's why I see a 1 over x. I mean, if you want, you could write this as integral sign, then 1 over x first, then times ln of x, then times dx. So it's really there. It's kind of just hidden how it's written, but this looks like it's going to work out. So as usual, we need to solve for dx, multiply by dx on both sides first because it's in the denominator currently. So you have du is equal to 1 over x times dx. And then to solve for dx, often the approach people take is to divide both sides by 1 over x. That technically works. But, excuse me, but it's actually extra writing. Instead of dividing both sides by 1 over x just because it works, why not just notice you've got an x in the denominator of an equation? Why not just multiply both sides by x? And when you do that, you'll have x times du is equal to dx. That's going to be way nicer. So now we'll take the original question and make some replacements. When we see an ln of x, let's replace that with a u. When we see a dx, let's replace that with an x du. So those are the only replacements made, right? This ln of x became a u. There was an x down here. I just left that as an x. We'll see what happens, in a moment. The dx got replaced with x times du right there. And so now look, the x's cancel, and we're left with integral u du. In other words, integral of u to the first power du. We need to anti-differentiate, so raise the exponent by 1, and then divide by the new exponent. So u to the 2 over 2 plus c. And then one last thing here is the original question didn't have u's in it. So we should go back and replace every u that we see with an ln of x. Just to be safe, it makes sense to put this in parentheses. So we're clear what we're ln'ing. So it's ln of x. And that result is going to be squared to copy this account for the exponent, divided by 2 plus c. What I would like to do, though, is compare this to a very similar looking question. So I have the space on the bottom half of the slide. Antiderivative of 1 over x times ln of x dx. Now, watch the wording here. This is x times. There's one multiplication sign that's hiding right there. 1 and 1 only. It's not x times ln times x. This is the kind of mistake that people make in thinking about this, and then other things go wrong because of reading the question incorrectly. It's x times ln of x. If you want, that x is in parentheses. It's of as in f of x. It's the name of ln is the name of a function. It's going to turn out, as strange as it is, even though this question and the question up there are different, the same u is going to work. So I'm going to pick u equals ln of x again, and I don't want to rerun through all this same work. I'm just going to copy it, and to save space, I put this sideways. But all this same, if the same u is going to work, then all this stuff that was just based on selecting u should all be the same. Now let's take the original question, just copied it down there, and make the replacements. So take a look. There's integral sign, 1 over, the x that was down here is still there. ln of x that was down here is replaced with a u down there. The dx got replaced with x du as before. And take a look again, the x on top and bottom cancel. And we're now left with integral 1 over u du. This is a different problem than we had up here. But let's think about, we had an antiderivative rule for 1 over u. This is going to be ln of absolute value of u plus c. And then the u here gets replaced with ln of x. For emphasis, I even put that of x in parentheses. You could drop the parentheses here if you want, but it's ln of absolute value of ln of no absolute value of x, close absolute value plus c. The error that I have seen people make in a question like this is to incorrectly say ln of absolute value of ln of absolute value of x, close absolute value plus c. This, I would say, is overcompensating, right? So here's, I think what sometimes happens is people get in this mode where they think, oh, if I'm doing integral things or antiderivative things and I ever see an ln, automatically it's always got to be an absolute value. And that's not necessarily true. The place where there's an absolute value appearing is right here, because that's how that antiderivative, the official antiderivative rule, went like that. That the antiderivative of 1 over u is ln of absolute value of u plus c. That's the only place, right? So this u here that's inside the absolute value gets replaced with ln of x without an absolute value, because, well, that's what u was here. It's the same reason in the earlier question up here, u was ln of x, and notice u just got replaced with ln of x. And so there's no absolute value at all in the question up here in the top half of the slide. U just should get replaced with what it literally gets replaced with. U is equal to ln of x. And so same deal here, right? Like sometimes people kind of work too fast. I hope this is making sense that in both cases, the u should just get replaced with ln of x, not with ln of absolute value of x. Right? So be very, very literal in the replacements that are made. The only time we had an absolute value was because that's how the official antiderivative of 1 over u went. Okay, this literal replacement idea you're going to see in the next question. So I've got now a rather challenging integral question that's going to require substitution in sort of a creative fashion. This one's kind of new in terms of idea. So let's look at antiderivative of the fraction 10x to the fourth plus 6 over, the denominator is 9 raised to the power. Sorry if it's hard to maybe see, but that's underlined there is the exponent. So 9 raised to the exponent. The exponent is x to the fifth plus 3x. Oh yeah, and then a dx. All right, so there's a lot going on in this, and as usual, this is an antiderivative question, meaning if you can directly answer the derivative of whatever, the derivative of fill in the blank is this, great, do it. But I don't see it. Like the derivative of what thing is the thing that's circled? I don't know. So this usually means, unless there's some algebra thing to do first, and then you would see it, this usually means substitution. So the substitution I'd like to make is the exponent that was there. So u is equal to x to the fifth plus 3x. So the derivative, one term at a time. First of all, the first term is real nice to take the derivative of using the power rule. So d over dx is 5x to the fourth plus, and then 3x is going to differentiate to a 3. As usual, solve for dx. So since dx is in the denominator, you need to multiply by dx on both sides. du equals, here parentheses would matter, right? Let's be very clear about what's going on with order of operations, because of the multiplication. So quantity 5x to the fourth plus 3, close parentheses, dx. And then one final thing to solve for dx, just divide both sides by what's in parentheses. So we have du over 5x to the fourth plus 3 equals dx. Okay, let's make some replacements then. So back to this original question. When we see an x to the fifth plus 3x, we can replace that with u. Where we see a dx, we can replace that with this fraction du over 5x to the fourth plus 3. So it'll look like this. It's kind of messy, but I'm trying to be as literal as possible and just go through the steps as uniformly and as consistently as possible. So integral sign, 10x to the fourth plus 6 over 9 to the, and there's our first replacement. 9 to the, instead of writing x to the fifth plus 3x, that got replaced with a u. The dx got replaced with this fraction here. Okay, now as written, there's this mix of x's and u's. We're hoping stuff cancels out, and people will make up all kinds of things at this point. Please be careful with your algebra here. I've seen people do things like take that 6 and 3 and then put like a 2 there. You can't do this. Okay, so the reason you can't cancel the 6 and the 3 is because of the plus signs, right? The only things that cancel in a fraction are factors that appear on top and bottom. So um, this doesn't cancel with this, not as written. But if the only things that cancel are factors, well, and the process of factoring, the factoring process produces factors. Let's factor. Take a look at this numerator, 10x to the fourth plus 6. You can factor out a 2. So the only algebra step that occurred here, it's an algebra step, so you'll find this integral symbol is still written. I rewrote the numerator by factoring out a 2 as 2 times the quantity 5x to the fourth plus 3 over still, and then all the rest of the stuff here is the same. 9 to the u times du over 5x to the fourth plus 3. In now that we've got this factor, right? So that entire thing in parentheses is a factor. Over here as well, 5x to the fourth plus 3 is technically a factor because anything, the entire denominator of a fraction is always in a hidden set of parentheses. And if you want to like really see it as factor, you could put it as a times 1. But now the point is the factor of 5x to the fourth plus 3 on top and on bottom cancel. Now, sorry, all this writing probably gets in the way of seeing what actually happened here. But if the 5x to the fourth plus 3 factor on top and on bottom cancel, we're just left with this. We're left with integral sign 2 over 9 to the u, and then just the du. Now, this is, I think this is a very stark example that like really shows why we do substitution and why this is useful. Take a look at this original question over here. Oh, what a mess, right? And compare that to this problem. At least, I mean, this one's not so good because there's still a mix of u's and x's, but this one's all in one new variable, u. And that's the whole point of substitution. We have not done an antiderivative yet. We still need to do that. We still need to find an antiderivative. But before doing that, it's just the whole point of this u substitution is this u is a bookkeeping process. It's like, would you rather look at this problem and do the antiderivative, or would you rather look at this problem and do the antiderivative? And the answer is very clear that I would want to pick this one because it's way smaller, right? But we're still not done. First of all, this 2. So we still need to find an antiderivative. The 2, you can certainly bring it in front. But then an antiderivative of 9 to the u, well, we have that if the 9 to the u were in the numerator. And just moving this 2 in front doesn't magically bring the 9 to the u into the numerator, right? If you want to rewrite this, you're going to need, so bring the 2 in front, but you'll need 9 to the negative u. Remember something that's in the denominator, we write this as 9 to the negative u. And then still a du, still written. But here's the thing. We have an antiderivative rule for 9 to just the variable, not 9 to the negative variable. So for exponential functions, we have an anti-differentiation rule, but the exponent needs to just be the variable itself. We don't have that. We have a negative u. We just want a variable there. This is where we're actually going to do a substitution, or rather, I guess we should say another substitution. So I would just want there to be a variable right there, where there's the negative u right here that I just circled. I want there to be a variable only. So let's assign that a new variable. Now, I don't want to write u equals. That'll be confusing because we already used u. So I'm using a v here. But where this spot where there's a negative u, in a moment, we're going to just have a new variable. It's going to just be a v there because, well, I picked v to be negative u. So check out what happens picking v to be negative u, sort of the same type of process here. Take a derivative. So dv over du equals negative 1. When you differentiate negative u, you get a negative 1. Now we need to solve for du, so multiply by du on both sides. So dv equals negative du. We're still not quite done solving for du. Multiply both sides by negative 1 is preferred over dividing both sides by negative 1, even though both work. So negative dv equals du. Now let's take this problem. 2 times integral 9 to the negative u du, and let's make some replacements. Right, so the 2 is still copied, integral sign is still copied, 9 to the, now the negative u got replaced with v, and then du got replaced with negative dv. Now I didn't want it to accidentally look like just 9 to the v minus a dv, so I put it in parentheses. There's technically this times negative 1 times dv, so I just brought the times negative 1 all the way in front of the integral and wrote this as negative 2 times integral of 9 to the v dv. Okay, now see that's what this replacement v equals negative u did for us. Now we've got an exponential function where we've got 9 raised to that, and then the exponent is just the variable. So now we can apply our exponential anti-differentiation rule. So copy the negative 2, and then the antiderivative of 9 to the v is 9 to the v over ln of 9. Oh yeah, we've now found an antiderivative, so we have a plus c here. Okay, so this is the stage going from here to here where we found an antiderivative, and now we're not done because the original question didn't have v, so we should replace v with negative u, so negative 2 times 9 to the negative u over ln of 9 plus c. But the original question didn't have u either, it had x's, so let's just go back and replace the u with x to the fifth plus 3x. Now that replacement here, due to order of operations, needs to be in parentheses. Or if you want, you can distribute this minus sign, but I think it's more literal and kind of easier to spot what's happening just to do negative and then replace what u was in parentheses. So final answer, negative 2 times 9 to the power negative quantity x to the fifth plus 3x, and then ln of 9 in the denominator, and then plus the c afterwards. So we're done with the question, but like there's usually lots of questions related to this, so let's wait for a moment. How we doing? There's usually like a question of like, oh wait, how did you get from this step to this step? So I just want to wait for a moment, see if we're kind of okay with this overall. What happened here was 2 substitutions. We really all doing okay with this? I just usually a question like this brings up lots of questions, so I just want to make sure we're okay. How did you get the ln of 9 in the bottom was a question that came in. So the thing is, this right here turns into this due to the standard anti-differentiation rule. So you got to go back and look. I want to say uh, it was reviewed or formally introduced last Monday. So look at the slides from then, and it was previewed the Thursday before that. But I'll just comment that. Let me try to quote it. I might not be using exactly the same language, but if b is fixed, then the antiderivative of b to the x dx equals b to the x over ln of b plus c. So that was used to convert what's in this box to that box, the b being 9, and instead of x being the variable as was presented in the box when we first learned it, it's the variable is v here instead. Does that help address the question? Okay. Other questions? Yeah, these are the kinds of things, like there's lots of, and again, yeah, it's like, so yeah, somewhere in the process of this double substitution, also there's this reminder of how the exponential anti-differentiation rule happens. I'll just pause for another minute, see if somebody else wants to ask something. I will, I guess, share my opinion that I think a question of this kind is challenging and time-consuming, right? And you shouldn't expect to see something like this on Thursday's exam. I mean, in principle, yeah, but like let's not, not this Thursday. Maybe on the final, right? And maybe not, right? But the point is, I needed to talk about this because you will likely see this method occur in homework. And it is challenging. It is time consuming. But like all of the things we've seen up until now today are ideas that hopefully help kind of rehash and help reinforce the ideas that we saw last week. Substitution itself, I think, is quite a challenging process. The reason I'm saying all that and trying to create a break is that the remaining, I know that we spent 33 minutes already on these things that are, in a sense, review and so on. I'm saying this because for the last 21 minutes of class, we're going to do something new. Like, this is new stuff, and this new stuff that we're talking about starting this moment is not on Thursday's exam. So what we're going to look at, we have been looking at the indefinite integral. The new thing we're looking at is called the definite integral, and the notation looks really similar, which is why I want to be clear. You still have this integral sign. You still have a function. You still have a dx. The difference now is there's these two extra thingies there, and they're called a and b generically, but they're actually numbers in problems. We'll see in a moment. So what happens now is this new thing. How is it defined? You're given a function, y equals f of x. You're given two x values. So x equals, right here, that's an x value. It's just generically called an a. And then you have another x value called b. And this new thingy called the definite integral is the area, technically the signed area. We'll get to that in a second. It's the area between the graph of the function y equals f of x and the x-axis, and then the two vertical lines x equals a and x equals b. Sorry for the placement of this. I'll get that fixed when I repost these. So this is an overall picture of what this is supposed to be. So like you've got, just in general, you have the x-axis and you have y-axis, and then you have the graph of some function, right? You typically have some wavy function. That's your function y equals f of x. And this is a curve, right? This is not a straight line. It's curvy. And then, so in addition to the x-axis and the graph of the function, between those two regions, you're also given x equals a and x equals b. So you have, that might be the vertical line x equals a, the vertical line x equals b. And so you have this one enclosed region here, and that shaded region right there, that area, how much paint is needed there? That is what this definite integral thing is representing. Now it's a signed area. What does that mean? So signed area is trying to say that any of the shaded regions above the x-axis are positive areas. And regarding signed area, here's another example, another picture. Any regions below the x-axis are considered negative area. This is really strange. You've thinking about algebra and geometry, we never talk about area being negative. But in calculus, when talking about the definite integral, when you're talking about this thing, so here's a function, different function. I needed to pick a different function to illustrate. So in this second example, here's a function, and then here's the x-axis. So the region between those two, and then between x equals a and x equals b, there's this shaded region. But this shaded region is all below the x-axis. And it's because, well, the graph of the function was below the x-axis. So this shaded region was below the x-axis. So in this example, for this function, this shaded region, it all counts as area negatively. Which sounds strange. And just one more picture before we dig into concrete examples. I have this function. It has this kind of big hump like this, and then this tiny little dip down here below the x-axis. And I've picked, to illustrate the point, I've picked the x value a over here and the x value b over there. And now what happens is there's two enclosed regions. There's this shaded, much bigger region above the x-axis, and there's this tiny sliver of area that's below the x-axis. So in this picture, you have both a positive area and a negative area, but the positive area is much larger. So overall, for this function, this definite integral is going to be, overall, the answer is going to be a positive answer because you have a big positive number, you add to the rather tiny negative number, so overall you'll have a positive number. Okay, this all sounds a little, let's put it this way. This all sounds a little abstract right now because we just have this kind of, this curvy, this function f of x, and it's like, what? So to outline where we're headed this week, we'll practice more of this idea tomorrow with concrete examples. We'll end on concrete examples today. We'll practice more concrete examples tomorrow. And here's the strange thing about this. On Wednesday, even if you have a curve like this, we're actually going to talk about finding the area. Okay, that's Wednesday's topic. But today, to like just clarify what the heck this means, we're going to look at some examples where you don't have a curve. Okay, you have straight lines. So here's our first concrete example to like really help illustrate what the heck this means. So we have what's called the definite integral from 2 to 8 of 5 dx. So in the past we had the indefinite integral because there was no 2 here, there was no 8 there. And in the past we would have done an antiderivative problem. Now with these two x values, one of them being 2 and the other being 8, we have an area problem, a signed area problem. So just because it's new, normally wouldn't bother writing all this stuff, but I just want to clarify that the function here is this part where the 5 is. So the function is f of x equals 5. Or if you graph this, y equals 5. The output is always 5, no matter what the input is. That's a constant function, right? The y value is always 5. It's a horizontal line. That's what the graph will look like. We have x values of 2 and 8, and we'll graph. So here's the x-axis down there. Here's the y-axis, and the line y equals 5. That's the graph of the function. Okay, the graph of the function is not wavy, it's a perfectly horizontal line, and we're looking between the x value of 2 and the x value of 8. That's going to create the shape of this rectangle. So we want this signed area, this rectangle, this pink rectangle is above the x-axis. So the rectangle, by the way, has a height of 5, right? Shown like right there. So starting from the origin all the way up to where 5 is. The width, though, is 6 because that's going from 2 to 8. So you have to do 8 minus 2, right? Think about it. If you're standing on a ruler right where the 2 tick mark is and you would need to move over to where the 8 tick mark is, you just move 6 units to the right. Okay, so height of 5, width of 6. The area of this rectangle is 30, of course, right? And so to answer this question, we'll have a new method on Wednesday, but just we need to get started by making this as concrete as possible with some geometry, using our geometry area formula for a rectangle. The answer to this question, the signed area question, is going to be 30. Hope we're doing all right with that one. Okay, the next one, another example of this. So another definite integral problem, or another question about signed area. Now we have the definite integral from 3 to 12 of negative 10 dx. Again, in general, I don't expect people to bother writing down all of these details, but since it's new, I want to connect it back to the definition we were just given. The function in this example is f of x equals negative 10. If you graph the function, which we will do in a moment, that graph is also a completely horizontal line. That's the y coordinate is always negative 10, no matter what the input x is. So regardless of the input, the y value is always negative 10. That creates a horizontal line. The x values are 3 and 12. So if we graph this, sorry for how the picture went. I'm going to see if I can try to tweak how the system is drawing this later, but there's the x-axis. Here's the y-axis. Over down here is the graph of y equals negative 10, perfectly horizontal line. That's the part that I was a little bothered by, but the tick marks are 3 and 12. The rectangle itself is getting in the way. So x equals 3, x equals 12. That's what this information here is supposed to give away. This 3, little 3 and little 12 next to the integral sign. I know this is new. We haven't seen anything that looks like this before today, but that's telling you x equals 3, x equals 12, those vertical lines. So that region creates this pink rectangle, but that rectangle is below the x-axis. Okay, so this is going to be a negative area. But just to talk about what is this rectangle, first of all, the height of this rectangle is 10, right? This distance along here is 10, because if you start at the origin, you walk 10 units down to get to that tick mark. So that should be this left side of the rectangle is 10. The width of the rectangle is 9, right? Because you've got this tick mark of 3 and you have this tick mark of 12. So if we sort out, yeah, the distance. So to get the width, it should be 12 minus 3, which will give you this 9. Okay, so look, this rectangle in a geometry sense, we just say has an area of 90, right? 10 times, sorry, there was, there's something going on outside. I don't know if that's thunder or a fighter jet or something. So sorry, I had to just pause. I got distracted. Okay, so we have the rectangle's area in the sense of geometry should just be height times width, or 10 times 9, or 90. However, because this region is shaded below the x-axis, um, since the shaded region is below the x-axis, we count this area as negative. In all of these types of problems, the signed area it's negative. So there's a question again from the top, but then I stuck in a minus sign and said 10 times 9 as a reminder that we're doing the area of a rectangle. So final answer, negative 90. Okay, so we had an example where the region was above the x-axis, and one where the region was below the x-axis. In the next problem, you're going to see a definite integral again. So you're going to see integral sign, you'll see 2x values again, and the function is no longer going to be a completely horizontal line. It's going to be a different function. So we won't have a constant function in this next problem. I've got integral -2 to +5. The function is f of x equals 3x dx. Again, because it's new, just identify the pieces. The function is f of x equals 3x. That's not a horizontal line. It's a line. It's just not a horizontal line. The x values we have are -2 and +5. So let's draw a picture. By the way, just to preempt and answer a question that people will probably ask is, where did you get the y coordinates of -6 and +15? Where did those come from? Well, if you plug in this x value of -2 in, you'll get -6, and you plug in this y value, sorry, this x value, the other x value of 5 in, you'll get 15. So the y coordinates that you're going to see in the picture in a moment of the y coordinates -6 and +15, they come from applying the two x values into the function. Here's the picture, right? So here's the x-axis. Here's the y-axis. The function is 3x. In other words, y equals 3x. If you want, that's a y equals mx plus b, right? So it's a line this line here has slope 3 and goes to the origin because the y-intercept is 0. That's the b, right? I don't want to call it b because b is being used for something else right now. But the y-intercept is 0. That's why it goes to the origin. So we have the graph of the line, and then so we want the region or actually it's plural, the regions between the graph of the line, the one line that's thickened in the picture here, and then the two vertical lines when x equals -2 and x equals 5. So here's x equals -2, here's x equals +5, and there end up being two regions. There's two regions that are between the graph of the function and the x-axis and these two vertical lines. So there's a region in yellow and there's a region in pink, right? So the yellow, let me get rid of too many markings probably right now to see what's going on. The yellow region is above the x-axis, so that should be counted positive. The red region is below the x-axis and should be counted negative. So the positive region, it's a triangle. That's why I wanted to pick a straight line for now. We'll look at new, more creative examples tomorrow. But this triangle, so positive area, use the triangle area formula, 1/2 times base times height. So this height 15, that's why we needed the y coordinate, right? So this triangle, the height there is 15, right? Yeah, 1/2 times base times height. And then for the other little red or pink triangle here, it'll be a negative area. Let's compute the area first as 1/2 times base times height. So this distance there is 2. This distance is 6, without worrying about minus signs yet. So we have just in pure area terms, geometrically, we have 1/2 base times height, 1/2 times 2 times 6. But we will need to count that negative. So here's how we put it all together. There's the original question up here. Again, it's about signed area, and I just stuck the positive area first. And the negative area, it should be plus a negative, but I just wrote it as minus, and then that area in red. So I want to just pause here, see if we're okay with this overall. Okay, let me then say the following. What I want to do is there's this danger that this new concept today, the definite integral, can get confused with the old thing, indefinite integral. So I'm going to take a couple minutes to just compare and contrast indefinite integrals and definite integrals. So first of all, indefinite integrals, this is this is on exam 4, right? This is on the exam dated for Thursday, even if you do it on Friday. Definite integrals, this is new as of today. This is not on exam 4. Not on exam 4. And the notation looks so similar, which is why I want to go over. This is what an indefinite integral looks like, and here's what a definite integral looks like. How do you tell? How do you tell these apart? First of all, this indefinite integral has no endpoint. So over here and right there, at the very bottom and top of the integral sign, there are no numbers written there. For a definite integral, there are numbers. This little a and little b are specific numbers in specific problems, and those things are called endpoints. So x equals a, x equals b, those are provided. If you see those, that's a definite integral. That's not on this, not on exam 4. It'll be something, for the final exam. You should expect to see this type of thing on exam 4. And here's the other thing. I know you might be like, well, why even have notation that looks so similar? It looks confusing. I get it. The thing is, the connection between these things we talk about on Wednesday. So let me just say some things to try to clarify that these are different for now. First of all, the final answers are different. In the indefinite integral, the problems we've been looking at, you get a function with a plus c at the end of it. It happens to be an antiderivative. That's what this function represents. And that's what indefinite integrals are. Versus over here, this new thing, the definite integral, the final answer is a number, and that number represents signed area. So those are rather different. A function with a plus c as a final answer versus just a number. So as an example, here's this could be exam 4 relevant. It's like this is asking what's the antiderivative of 2x, and that should be 2x. Sorry, that should be x to the 2 plus c, right? This is an antiderivative problem. This is one that doesn't require substitution. If I take that same, almost the same question type, make it look as similar as possible, I just copy pasted and then I stuck in the 0 and 6. Now this is the new thing. This is a definite integral problem. And so I drew a picture down here of this slanted line is y equals 2x. And then I just went from x is 0 to x is 6, so that the shaded region is going to be this pink triangle there. And that's going to be 1/2 times base times height. I don't usually simplify all the way down to a number. I just usually leave it like this. But to illustrate the point right now, you get a number here, 36. This number 36 represents the area, whereas the final answer here was a function with a plus c. So I know the questions look so similar, but the final answers here and here are actually really different. And the connection between these, actually is one, is the topic of Wednesday's class. Tomorrow what we're going to do is continue with more examples of definite integrals, just to really emphasize the idea that this thing should be thought of as a signed area. Just to do the quick round of announcements here, it is exam week again, so please do the online quiz on Tuesday, but there's an online quiz for Tuesday. There's a pre-exam inventory assignment for Wednesday, and Thursday is the official date of the exam. We will not have a live class session on Thursday morning, but you can do the exam in any 5-hour window of time that you pick between Thursday and Friday. And please start WebWork 38. All right. We'll end it with that a little early. See you in office hours or see you tomorrow.